We are Group 4, and today we are presenting the design of a record player for manufacturing and assembly. In my group is Marco, Caitlin, Colin, Raymond, and myself. A record player is a mechanical device that plays audio from a vinyl record. It works by capturing unique grooves that produce vibrations that occur at individual frequencies. Its primary components consist of a vinyl record, stylus, turntable, and a cover. The annual estimated demand is approximately 50,000 units per year, and for reference, there were 82,000 record players that were sold in the U.S. in 2021. Primary customers generally represent the mass market, who may be casual music listeners, hobbyists, or aesthetic buyers, whereas secondary customers are more involved and in tune with the product, who may be serious music listeners, audiophiles, vinyl enthusiasts, or old-timers. This fast diagram shows the main function as play audio. The two subsets of that function is to produce sound and to amplify that sound. And to produce sound, you would rotate the record, which is driven by the motor, and to convert the vibrations into sound, which is done by following the grooves. To amplify sound, you will need to increase the phono signal. Some of the other functions include assuring dependability, which can be done by preventing scuffing, assuring convenience, enhancing the product. Some of the examples include pausing sound and controlling the volume and pleasing senses.
So moving on, here's our function component mapping matrix. As you can see, most of the components are related either to the following the groove function or to preventing scuffing. And the majority of the components are related to more than two functions, with some more specific components being responsible to fulfilling only one of the functions.
Now we will be discussing the product family design. The functional differentiation table was created in regards to our fast diagram and the two customer groups that we established earlier. The two functions that were different in the customer groups were prevent scuffing and please senses. This is because the second customer group is much more focused on quality and lifetime span of the product, while the first customer group is much more focused on convenience. The modules that particularly pertain to these two functions are the tone arm and the aluminum platter, as those will be the things that we are looking at to improve on.
For the design for manual assembly, we had the platform part as the dust cover and the module part as the tone arm, as they both have high manufacturing costs as shown in the quad chart. For the dust cover, we added two hinges with U-shaped notches to allow for a snap fit to the base and to reduce the need for fasteners. This also allows us to orient the cover to the base, helping with DFA 2, 3, 11, and 7. For the tone arm, we combined it with the tone arm connector as one coherent part to help with DFA 1 and allow us to orient and snap fit the tone arm connector to the base more easily, as shown in 3, 11, and 7.
Here's the manual assembly analysis both pre and post DFA. The modification of the platform part, the dust cover, reduces total assembly time by making it easier to insert and eliminating the need for two screws and nuts. However, the part manufacturing cost increases slightly as a result of adding material. Product function is not affected. Combining the tone arm with the tone arm connector and making it a snap fit reduced both the screw count and part count. Manufacturing cost and product functionality are unchanged. Overall, the modifications significantly reduce assembly time from 179.8 seconds to 126.54 seconds. And assembly efficiency was increased from 0.2503 to 0.3319.
For the design for automated assembly, we chose the feet, the start-stop buttons, and the central pin as part of the base subassembly, as they are small, lightweight, and will be used for insertion, orientation, and feeding. For the start-stop buttons, we added features to allow for easy insertion, which also assists with facilitating orientation during feeding. For the central pin, we did the same, extending the geometry to allow for different orientation and to provide locating features for assembly processes. And for the feet, we did the same by adding a screwing mechanism to the feet to reduce the need for fasteners and to allow for more locating features. On this slide, we have the exploded view with the new feet, central pin, and start-stop buttons to demonstrate the change in the automated assembly process.
Here's the pre and post DFA automated assembly analysis. The modification of the foot eliminated the need for screws, the central pin became easier to handle, and the start-stop button became easier to insert. As a result of these changes, the total price fell from 1.64 cents to 0.53 cents.
For the dust cover, we chose to make it out of acrylic PMMA. We chose this as it should be light and scratch resistant. The shape of the dust cover should be 3D hollow with a mass of about 600 grams, a section thickness about 3.6 millimeters, a standard tolerance of 0.5 millimeters, a surface roughness of not critical as it doesn't need to house anything specific, and an economic batch size of 100,000. Out of the processes, the two processes that work was machining and injection molding, and we selected injection molding for this process. The next piece that we will be looking at for process selection will be the tone arm. Now, we decided to make it out of aluminum alloy as it is light while also has a lot of wear resistance. The shape of the tone arm is a 3D solid with a mass of 111.54 grams, 1 millimeter section thickness, a 0.1 millimeter tolerance as it has to be very specific, critical surface roughness as it has to connect to the needle, and an economic batch size of 100,000. Out of these options, we decided that machining was the best possible option as everything else fails.
Next, we selected two components of the record player assembly to improve for design for manufacturing. We specifically chose parts that were variously manufactured so that we could evaluate them and take recommendations from DfM Pro. The first part is the dust cover, which is an injection molded plastic part. In DfM Pro and SolidWorks, I took the newly designed dust cover with the two snap fit hinges and recorded the dimensions as well as calculated the total cost per part, which came out to $2.67. After evaluating, DfM Pro recommended adding draft angles to the inner and outside walls in the draw direction, particularly greater than 1 degree, as well as adding draft angles to the snap fit hinges. The reason for this is that proper draft design helps with easier part injection, shorter cycle times, and better productivity. Once those draft angles were added, the dimensions were recalculated and the width and subsequently volumes were decreased. This decrease led to a total cost of $2.61 per part, which leads to a 6 cents cost reduction per part by designing for manufacturing.
Now, moving on in our DfM section, we analyze the tone arm, which is a machine part made out of aluminum, which originally had a total cost per part of $9.42. After analyzing it using DfM Pro, several design changes were suggested, such as the one highlighted in this slide, as removing unnecessary holes and keeping the radius of shafts even. Taking into consideration the changes suggested by DfM Pro, the original tone arm CAD file was modified in order to allow for a more straightforward and efficient machining process. The changes made were increasing the radius of the main shaft, removing the top pin part, and removing the hole around the bottom pin part. After these changes, we could get to a reduced total cost per part of $8.78. Finally, when looking at a price analysis between the pre and post DfM design, using both the analytic method and hubs, our quotes for individual part costs are lower for the post DfM design. The difference between analytical and hubs costs may mainly be due to some simplifications that were made when calculating for the analytical method, and due to the fact that extrapolation had to be used to get the hubs quotes.
In addition to all the redesigns of our product, we would also like to create an app that users can download on their phone either from the Google Play Store or the Apple App Store. The app would have a few different functions, including being able to start and stop the records while also simultaneously being able to flip over the records and play a whole new set of music. The record player would be able to Bluetooth connect to the individual device that the user was using and would allow for the stopping and starting of the record. This would help the user financially, as the starting and stopping of the record could help precisely time when you want to start and stop listening, which can save on the electricity bill. Additionally, potential revenue that could be gained through this app would be recommendations for music albums from artists that could be ads on the app itself.
In conclusion, we were able to reduce costs to $1.33, which helped with the cleaner design for manufacturing and for user management. However, it was a little simplified due to our CAD creation skills, which led to easier calculations. However, the simplicity could compromise the feasibility of the product, so we hope in the future to have more complex parts with better CAD skills.